Tonight, we're going to talk about something you've taken for granted your entire life. The sun. It's been rising every morning for as long as humans have existed. Every civilization, every city, every farmer and sailor and scientist has built their world around it. If you had to point to one thing that's guaranteed to be there tomorrow, it would be the sun. But here's what almost no one thinks about. The sun is changing. It's getting brighter. Slowly. Far too slowly for any person, any generation, any instrument we've ever built to catch in real time, but steadily and always in the same direction. And the consequence of that, played out over enough time, is this. The same planet, in the same orbit, can stop being a place where life can exist. Not because it moves, not because anything explodes, simply because the star above it quietly becomes more than that planet's systems can handle. It doesn't happen in one event. It moves through layers, plants, then air, then oceans, each on its own timeline, each driven by a different mechanism. Understanding that sequence is key. By the end of tonight, you're going to understand exactly how it unfolds. If you enjoy exploring questions like this with me, subscribing to the channel helps others find their way here too. Liking and sharing the video helps even more. Now, let's begin. Let's start with something most people have never had a reason to question. The sun feels like a constant. Your grandparents woke up under the same sun you're going to see tomorrow morning. The first humans to cross the land bridge into the Americas looked up at the same sun. The people who painted animals on cave walls in what is now France and Spain 30,000 years ago. Their days started with light you would recognize immediately. That impression is not wrong, but it's incomplete. The sun has been changing the entire time, not in any way visible to a single generation, or 100 generations, or even the whole of recorded human history. The change doesn't happen on human timescales, it happens on geological ones, the timescale of eroding mountain ranges and shifting continents and species evolving beyond recognition. And it runs in one direction only. The sun is getting brighter. Here's how it works. Inside the sun, hydrogen atoms are constantly being fused together under enormous heat and pressure. That fusion is what produces the energy, the light and warmth that reaches Earth. But as hydrogen fuses, it becomes helium, and helium is denser than hydrogen. As it accumulates in the core, gravity compresses the core more tightly. That increased compression raises the temperature. A hotter core drives fusion harder. And a star driving fusion harder is a star putting out more energy, more light, more heat, every year fractionally more than the year before. Researchers Schroeder and Smith modeled this in 2008. Their figure, the sun brightens by roughly 1% every 110 million years. James Casting, one of the most influential scientists in habitable zone research, uses the same number, 1% every 110 million years. On any human timescale, that is essentially nothing. No thermometer, no satellite, no record any civilization has ever kept comes close to detecting it in real time. But let it run. 110 million years is longer than the entire span from the last days of the non-avian dinosaurs to right now. Long enough for seas to open and close, for entirely new families of animals to emerge and go extinct, for the map of continents to become unrecognizable. And across that entire span, all of that transformation, the sun gets 1% brighter. Now stretch it to 1 billion years. That's 9 of those 110 million year cycles, roughly 9% extra brightness. 2 billion years gets you close to 20, and 20% more solar energy is not a warmer summer. It is a fundamentally different energy balance for the entire planet. The atmosphere, the oceans, the rocks, the living things on top of all of it, everything has to respond. The sun isn't racing anywhere, but it's walking steadily in one direction, and it has never stopped, and it never will until it runs out of hydrogen to burn. So why hasn't this already cooked the planet? If the sun has been brightening for 4.5 billion years, why does Earth feel stable? We do see the effects, just not in the direction you'd expect. 4 billion years ago, the young sun was roughly 30% dimmer than it is today. run the standard energy balance for that weaker star, and Earth's surface temperature comes out well below freezing. Not just cold winters, a permanently frozen world, locked in ice from pole to equator, with no liquid ocean. And yet the geological record doesn't show that. Ancient rock formations are full of evidence for liquid water. Early life began in it. The planet was warm. This is one of the most studied puzzles in planetary science, and it goes by a name, the faint young sun problem. The most widely supported explanation comes down to the atmosphere. Early Earth almost certainly had far higher concentrations of carbon dioxide and possibly methane than the air we breathe today. Those greenhouse gases trap outgoing heat. Under a weaker star, a thicker atmospheric blanket compensated. Temperatures stayed in a range where water stayed liquid and life got started. The planet passed that first test. But passing one test doesn't mean passing every future one. Early Earth's problem was not enough warmth. The challenge facing the far future Earth is the exact opposite. Too much incoming energy from a star that's been brightening for billions of years and will keep brightening for billions more. Same orbit, same planet, completely different pressure on its systems. And unlike the early challenge, which was handled by a thicker greenhouse atmosphere, the future one can't be answered the same way. As we'll see shortly, the way Earth's climate system tries to cope with a brighter sun ends up creating a different kind of problem entirely. A problem that hits the living world long before it hits the ocean. Right now, on any given morning, nothing tells you any of this is happening. The warmth on your face doesn't feel like evidence of a star quietly putting out more energy than it did last century. The blue sky doesn't carry a label saying the amount of energy arriving here from space has a history, and that history is not flat. The present moment is exceptionally good at hiding the long process it's embedded in. That's worth pausing on. Stable is a word that only means something in relation to a timescale. The sun is stable on human timescales, completely, utterly stable, by every measurement we've ever been able to make. But stable on human timescales and stable on planetary timescales are not the same claim. A passenger sitting still on a moving ship is genuinely still from their own perspective and genuinely in motion from outside it. Both are true. Neither cancels the other. The sun is not about to become dangerous. That is not how this works. The brightening is so gradual that Earth's systems have been adjusting to it continuously since the planet formed. The atmosphere, the oceans, the rock cycle, all of them respond and adapt, spreading their answers across millions of years. For a very long time, those answers are more than adequate. But adequate is not unlimited. Each answer the planet finds works until eventually it doesn't, and the sun keeps brightening regardless of what the planet does about it. The ocean gives a useful sense of how that buffering actually works. Water stores an enormous amount of thermal energy and releases it slowly. It smooths out short-term variation. A strong El Niño year doesn't melt ice sheets. A cold decade doesn't freeze the tropics. The ocean holds the climate steady, even as conditions gradually shift. The same is true of carbon locked into rocks, of gases cycling through the atmosphere, of ice sheets that store tens of thousands of years of climate memory in their layers. These buffers are enormous. They are real. They give the planet a resilience that, from inside any human lifetime, makes it look like nothing fundamental is changing. But they're not limitless. They spread out the response. They don't stop what's causing it. A clock ticking in the next room. You might not hear every tick, but the hands move all the same. Each small increase in solar brightness is individually too quiet to register. Added up over sufficient time, they accumulate into genuinely new conditions that the planet must live under. Not a single dramatic turning point. Not a year any person will point to. Just a slope. Gradual, continuous, and running in one direction since the beginning. From inside a human lifetime, that slope feels completely flat. It isn't. Draw a ring around the sun. Not too close, not too far. Somewhere in between, where a rocky planet could hold liquid water on its surface. Astronomers call that region the habitable zone. It sounds simple. It isn't. Because that ring is not fixed in place. As the sun gets brighter over time, the ring moves. The warm inner edge, the closest you can safely orbit without losing your water, shifts outward, and Earth doesn't move with it. That's the part most people miss when they hear the phrase, Earth is moving out of the habitable zone. Earth isn't moving anywhere. The orbit isn't changing. What's changing is the ring itself, as the star inside it keeps brightening. Earth stays put, the safe zone drifts outward, and slowly, over astronomical timescales, the planet finds itself closer to the inner edge than it used to be. To understand why that matters, you need to understand what the inner edge actually represents, what physically happens to a planet that crosses it. A wet planet orbiting close to its star gets warm. A warm surface evaporates more water. Water vapor is itself a greenhouse gas, so more of it traps more heat, which drives more evaporation, which drives more warming. The feedback amplifies itself. Meanwhile, water vapor that rises high enough into the upper atmosphere gets hit by ultraviolet radiation from the sun. That radiation breaks the molecules apart, splitting water into hydrogen and oxygen. Hydrogen is light. Light enough that, at the temperatures in the upper atmosphere, some of it has enough energy to escape Earth's gravity entirely and drift off into space. One hydrogen atom escaping is nothing, but this process runs continuously. Over geological timescales, the loss adds up. The ocean doesn't drain in a season or a century or a million years, but a long, persistent leak above the weather layer, running across billions of years, is not nothing. It is how a wet planet becomes a dry one. This isn't speculation. It's the standard physical mechanism for how the inner edge of the habitable zone works. In 1993, Casting, Whitmire, and Reynolds published one of the foundational papers on the habitable zone, where it sits around different types of stars and what physical processes define its edges. Their calculation wasn't a magic circle. It was a model. It depended on atmospheric assumptions, stellar properties, and the physics of how planets radiate heat. But it gave planetary scientists a rigorous framework for thinking about where surface water could survive over long periods. In 2013, Koparapu and colleagues updated those calculations. Their cloud-free model placed the water loss inner limit at around 0.99 astronomical units from the Sun. Earth orbits at 1.0 astronomical units. The gap between us and that inner edge, in a model with no clouds, is about 1% of the Earth-Sun distance. Now, cloud-free is an important qualifier. Clouds are one of the most consequential and most difficult variables in any climate model. Low, bright clouds reflect incoming sunlight back to space and cool the surface. High, thin clouds let sunlight through but trap outgoing heat and warm it. The net effect of clouds on a planet's energy balance depends on their altitude, thickness, and coverage. And getting all of that right in a model is genuinely hard. So a cloud-free result is not a final verdict. It's a baseline, a controlled case that strips out the complication. Add realistic clouds back in, and the numbers shift. But here's what doesn't shift: the direction. Every serious version of the calculation puts the warm inner edge on Earth's side of the map. Not on the far side, not comfortably distant, on this side. The uncertainty in the clouds changes how close the edge is. It doesn't put Earth in the middle of an open field. Think of it this way. You're walking along a path with a fence somewhere off to your right. It's foggy, so you can't see exactly how far away the fence is. Maybe 10 steps, maybe 30. You and a colleague disagree on the distance, but that disagreement doesn't mean there's no fence, and it doesn't mean the fence is to your left. It's to your right. You just don't know the exact distance yet. The warm inner edge of the habitable zone is the fence. The exact distance depends on cloud behavior, on how atmospheric circulation moves moisture around the globe, on how the upper atmosphere responds to a brighter star. Different models give different distances, but all of them agree on which side of Earth it's on, and also on what happens to it over time. As the sun keeps brightening, the edge moves outward, slowly, continuously, always outward. In 2013, Rushby and colleagues added a crucial dimension to how researchers think about this. Rather than treating the habitable zone as a fixed map you're either inside or outside of, they treated it as something that evolves as the star ages. A planet doesn't just have a position in the zone, it has a history in the zone. It enters at some point in the star's life. It may spend billions of years well within the boundaries, and eventually it approaches an edge. That edge is not static. It tracks the brightening star. Their framework gave scientists a way to ask a more useful question than, is this planet in the habitable zone? The better question is, how long has it been in there, and how much time does it have left? That reframing matters because the word habitable can give a false impression. It sounds like a binary. You either qualify or you don't, and once you qualify, you're fine. Real planets don't work that way. They don't cross an edge and immediately transform. Conditions shift gradually. The atmosphere changes before the ocean disappears. The living surface changes before the rock becomes inhospitable. There's no line in space where everything flips. There's a long, slow process of conditions moving in one direction. The habitable zone is not a safe zone. It is a zone where the conditions for surface liquid water are possible, given certain atmospheric assumptions. Whether those conditions are actually present and how long they last depends on everything the planet is doing. Its geology, its carbon cycle, its biology, its cloud cover. The zone is not a guarantee, it is a starting point for analysis. What the moving zone makes clear is this: habitability is not a permanent property of a location, it's a relationship between the star, the orbit, the atmosphere, the ocean, and the living surface that has to be continuously maintained, and one side of that relationship, the star, keeps changing. That is why Earth is in the habitable zone is both true and insufficient as a description of Earth's situation. It accurately describes where things stand right now. It says nothing about where they'll stand in 1 billion years or 2 billion, even if the orbit never changes by a single kilometer. One astronomical unit is not a promise. It is a measurement. What the measurement means depends on the brightness of the star at the center of the system, and that brightness has never been fixed. Earth is obviously habitable right now. Oceans cover most of the surface. The air is breathable. Life has colonized every environment from deep ocean vents to high-altitude glaciers. Nobody is arguing otherwise. But here is something worth looking at more carefully. Earth doesn't sit in the middle of the habitable zone. It sits near the warm inner edge, not dangerously close on any timescale a human civilization would care about, but close enough that where exactly that edge sits and what it depends on matters a lot for how we think about the planet's future. When we say close here, the units are geological, not the next century, not the next million years. We're talking about closeness on a timescale where the natural units are hundreds of millions and billions of years. On that scale, the position of the warm edge relative to Earth's orbit is genuinely relevant. Kaparapu and colleagues put a number on it in 2013. Their cloud-free model placed the water loss inner limit at around 0.99 astronomical units from the Sun. Earth orbits at 1.0. That's a gap of about 1.5 million kilometers, which sounds large until you consider that the Sun's habitable zone spans hundreds of millions of kilometers, and Earth is sitting within a few percent of one edge of it. But cloud-free is doing a lot of work in that sentence, and it's worth unpacking. Climate models come in different levels of complexity. The simplest kind treats the atmosphere as a single vertical column. You calculate how radiation moves up and down through layers of gas, and you get a surface temperature. It's a clean, tractable calculation, and it's been enormously useful for understanding the basic physics of planetary climates. Kaparapu's model is in this family. The problem is that Earth's atmosphere is not a column, it's a globe. Air moves horizontally across it. Some regions have rising air, warm, wet, full of water vapor. Other regions have descending air, drier, cooler at altitude. The tropics and the poles behave differently. The upper atmosphere above the subtropics behaves differently from the upper atmosphere above the equator. These differences matter enormously when you're asking how much water vapor reaches the stratosphere, because the stratosphere is where water molecules are vulnerable to ultraviolet radiation and where water loss begins. And this is exactly what three-dimensional atmospheric models add. LeConte and colleagues ran a full 3D simulation of how Earth's atmosphere would respond to an increasingly bright sun. What they found was that dry, descending air in certain regions of the planet acted as a buffer. It helped keep the upper atmosphere drier than the 1D models predicted. That delays the onset of serious water loss. Wolf and Toon ran similar models and found the same thing. A realistically complex atmosphere keeps Earth stable significantly longer than simpler calculations would suggest. Those delays are real. They are not rounding errors. They shift the timescales we're talking about by potentially hundreds of millions of years. That matters. But they don't change the direction. The sun keeps brightening in every version of every model. The warm inner edge keeps moving outward. The delays buy time. They don't buy permanence. What 3D modeling does, beyond just shifting the timeline, is reveal which parts of the planet are doing the protective work. Dry, descending air at certain latitudes is one such mechanism. Cloud cover is another. Low, reflective clouds can significantly reduce how much solar energy the surface absorbs, and if a warming planet produces more of them, that feedback could extend habitability further. High, thin clouds have the opposite effect, trapping heat. The net impact of clouds on a warming Earth is one of the genuinely open questions in climate science, and the answer shifts the timeline considerably. Here is what survives across all the models regardless of those uncertainties. The warm edge is real, it's on Earth's side of the map, and it moves outward as the sun ages. The uncertainty is in the exact placement of the boundary and the exact pace of its movement, not in whether the boundary exists or which direction it moves. Now here is the part that most people don't think about when they hear the phrase habitable zone. They tend to hear it as a binary. Inside means safe, outside means not safe, a switch, not a gradient. Real planets don't work that way. The warm edge isn't one line. It's a series of thresholds, and they don't all trip at once. Different planetary systems, the carbon cycle, the biological surface, the oxygen content of the atmosphere, the water inventory, each have their own limits, and those limits are crossed in a specific order. The first major threshold isn't the disappearance of the ocean. It's the point where falling carbon dioxide concentrations make it too difficult for land plants to photosynthesize. That happens because the very process Earth uses to protect its surface temperature, pulling CO2 out of the atmosphere through enhanced weathering, also reduces the gas supply that plants depend on. The temperature stays manageable. The plants run short of raw material. After that, as biological productivity falls, the oxygen content of the atmosphere follows. Because oxygen at the levels we depend on isn't a geological constant, it's a biological product, continuously manufactured by photosynthesis and continuously consumed by oxidation reactions. When production drops, so does the atmospheric concentration. The ocean comes later still. Water loss through the upper atmosphere is a slower process than the carbon dioxide squeeze, and it takes longer to reach a critical state. What this means in practice is striking. Earth can remain blue from orbit, visibly covered in liquid water, looking from a distance like a world where life might exist, while already having crossed the first two thresholds. The surface water is present, but the conditions that made the surface useful for complex life have already been gone for a long time. Blue and green are not the same thing. A wet world and a living world are not identical. The ocean's presence doesn't guarantee that everything else is still working. You can feel none of this on an ordinary day. Standing outside, the air is comfortable, the light is warm. A tree nearby is pulling carbon dioxide through its leaves. Everything about the immediate scene is evidence that the system is functioning. That's because it is, right now, at this moment in the sun's lifespan. But Earth operates on two clocks simultaneously. The one you live by, meals, seasons, decades, and the one the planet lives by, measured in the slow loss of small margins in the upper atmosphere and the chemistry of the carbon cycle. Both are real, they just don't tick at the same speed, and that gap in speed is exactly why a stable afternoon can exist inside a planetary future that is, on the right timescale, anything but stable. The warm edge isn't approaching fast, but it is approaching, and when it arrives, it doesn't arrive all at once. We already touched on the faint young sun problem in the first part, the fact that 4 billion years ago the sun was about 30% dimmer. Earth should have been frozen solid, and yet the geological record shows liquid water and the beginnings of life. Now let's look at what actually solved that problem, because the solution is directly connected to the trouble coming in the far future. The answer was carbon dioxide. Carbon dioxide is a greenhouse gas. Molecules of CO2 in the atmosphere absorb infrared radiation, heat, that would otherwise radiate off into space. They hold it near the surface. The more CO2 in the atmosphere, the warmer the surface stays, all else being equal. Under a weaker young sun, Earth compensated by having much higher concentrations of CO2 in its air than we have today. That thicker greenhouse blanket kept the planet warm enough for liquid water, even with 30% less incoming sunlight. That's the basic answer to the faint young sun problem. But it raises a deeper question. If early Earth needed extra CO2 to stay warm, who was managing the supply? And who's been adjusting it as the sun has brightened over billions of years? The answer to that is one of the most important mechanisms in Earth's long-term climate history. It's called the carbonate-silicate cycle, and it was described in a foundational 1981 paper by Walker, Hayes and Casting. Here's how it works. Volcanoes continuously emit carbon dioxide into the atmosphere. At the same time, rainwater absorbs CO2 from the air as it falls, becoming slightly acidic. When that acidic rainwater lands on silicate rock, the most common type of rock in Earth's crust, it triggers a chemical weathering reaction. The products of that reaction, including dissolved calcium and bicarbonate ions, get carried by rivers into the ocean. In the ocean, marine organisms use those ions to build carbonate shells. When those organisms die, the shells sink and accumulate on the seafloor as carbonate sediment. Over millions of years, tectonic plate movement carries that sediment into subduction zones, where it gets drawn into the mantle. Heat and pressure eventually break it back down, and the CO2 gets returned to the atmosphere through volcanic activity, and the cycle begins again. It's a circuit. Carbon goes from the atmosphere into rock, and eventually back into the atmosphere. The full loop takes millions of years to complete. What makes this cycle a thermostat is the way weathering responds to temperature. When the surface warms, because the sun is brighter or because volcanic activity has released extra CO2, warmer air holds more moisture, rainfall increases, and weathering speeds up. More weathering means more CO2 pulled out of the atmosphere. Less CO2 means less greenhouse warming. The surface cools back toward a lower temperature. Conversely, if the surface cools because volcanic activity has quietened, or because CO2 has been drawn down too far, weathering slows, CO2 accumulates, and the greenhouse effect strengthens until the surface warms again. Nothing about this process looks like a thermostat from the inside. A raindrop doesn't know what the global temperature is. A weathering reaction on a hillside in what is now Brazil has no awareness of volcanic emissions in what is now Iceland. But the system as a whole, averaged across the entire planet and across millions of years, behaves like one. Under the faint young sun, this thermostat allowed more CO2 to build up in the atmosphere because cooler temperatures slowed weathering. More CO2 meant more warmth. The planet stayed above freezing. As the sun gradually brightened over billions of years, warmer conditions accelerated weathering, pulling more CO2 down. The blanket got thinner as the lamp got brighter. The surface temperature stayed in a habitable range. Earth adjusted, continuously, without anyone or anything directing the process. This is genuinely elegant. The same mechanism that could have let the planet freeze under a dim young star instead prevented that by leaving CO2 in the air. And the same mechanism prevented Earth from overheating as the sun brightened by pulling CO2 back out. For billions of years, it has kept surface temperatures within a range where water stays liquid and life can function. But now comes the problem. A feedback that protects temperature does not automatically protect every condition that life depends on. It protects temperature specifically, and the way it protects temperature, by removing CO2 from the atmosphere, has a cost, because CO2 is not just a greenhouse gas. It is also the raw material that every photosynthetic organism on Earth uses to build organic matter. A plant takes in CO2 through tiny pores in its leaves. Inside the leaf, that carbon is combined with water, using energy from sunlight, to produce sugars, the chemical foundation of the plant's growth, metabolism, and reproduction. This is photosynthesis. The plant doesn't care about the global carbon cycle or the long-term stability of Earth's climate. It cares about the concentration of CO2 in the air around its leaves. And if that concentration falls below a certain threshold, the chemistry of photosynthesis starts to break down. Different plants have different thresholds. C3 plants, which include most trees, most flowering plants, wheat and rice, struggle at lower CO2 levels than C4 plants like grasses, corn and sugarcane, but all of them have a flaw. Below a certain concentration, photosynthesis can no longer run efficiently. Growth slows, eventually it stops. So here is the trap that the carbonate-silicate cycle eventually sets for the living world. As the sun keeps brightening over the next billion years or so, the thermostat will keep pulling CO2 out of the atmosphere to protect surface temperatures. That's its job. It will do it the same way it's been doing it for billions of years, through the slow, distributed process of rain on rock, carbon into ocean, sediment into mantle. And in doing so, it will steadily reduce the atmospheric CO2 concentration toward the point where plants can no longer function. The climate system will keep the surface temperature in a reasonable range, and in the process, it will remove the gas that the organisms maintaining that surface actually need to survive. Place the early Earth and the far future Earth side by side, and the symmetry is striking. 4 billion years ago, dim sun, thick CO2 blanket, liquid water possible, life beginning. Far future, bright sun, thin CO2 blanket, liquid water still possible, life no longer able to maintain itself at the surface. The same mechanism sits at the center of both stories. In the first, it solved the problem. In the second, solving the problem is the problem. This is what makes the far future of Earth more interesting than a simple warming scenario. The planet doesn't just get hotter until everything fails. It actively defends its surface temperature, using a mechanism that has worked reliably for billions of years. And the cost of that defense falls on the organisms living on the surface, specifically on their access to the carbon they need to build themselves. The old solution becomes the future squeeze. The thermostat keeps working. The plants run out of what they need to keep working. And those two facts are not in conflict, they're connected. One causes the other. Pick up a wet stone after rain. It feels inert, cold, solid, doing nothing. But at the surface, in the thin film where water, air, and mineral meet, a chemical reaction is underway. Here's the mechanism. As rain falls through the atmosphere, it absorbs a small amount of carbon dioxide from the air. That CO2 dissolves into the water, forming carbonic acid, a weak acid, but acidic enough to react with certain minerals when it hits the ground. When that acidic rainwater lands on silicate rock, it breaks down the surface. Calcium and magnesium ions are released. Bicarbonate ions form. Those dissolved products wash downhill into streams, into rivers, and eventually into the ocean. In the ocean, marine organisms pull those ions out of the water to build calcium carbonate shells. When those organisms die, the shells accumulate on the seafloor. Tectonic subduction eventually draws that carbonate-rich sediment into the mantle, where heat breaks it back down, and volcanoes eventually return the CO2 to the atmosphere. That is the carbonate-silicate cycle which we covered earlier. But now let's look at what drives its speed, because speed is where the climate feedback lives. The key variable is temperature. A warmer surface means warmer air. Warmer air holds more water vapor. More water vapor means more rainfall. More rainfall means more rain on rock contact. More contact means more weathering. More weathering means more CO2 pulled out of the atmosphere. Less CO2 means less greenhouse warming. The surface cools relative to where it would have been without the feedback. That loop is the thermostat. It doesn't have a dial or a controller. It runs on rainfall and rock chemistry, distributed across every exposed hillside and mountain range on the planet. And as the sun gets brighter over the coming billions of years, that thermostat is going to be doing increasingly heavy work, pulling more and more carbon dioxide out of the air to keep surface temperatures in a manageable range. For the climate, that's good news. The surface stays cooler than it would otherwise be. Liquid water remains stable for longer. The feedback that has been operating since the early Earth continues doing what it's always done. For plants, it's a slow-motion disaster. Caldera and Casting worked this out in 1992. They took the standard model of how the carbonate-silicate cycle responds to solar brightening, and they asked a specific question. At what point does atmospheric CO2 fall low enough that photosynthesis becomes impossible for land plants? Their estimate placed the threshold for major plant stress at roughly 1 billion years in the future. Later research shifted the range. Graham, Halevi, and Abbott found that if weathering responds more strongly to CO2 concentration itself, rather than just to temperature, then plants could survive somewhat longer, potentially out to 1.6 billion years or beyond. But in every version of the calculation, the direction is the same. A brighter sun drives the carbon cycle toward lower atmospheric CO2. Lower atmospheric CO2 eventually reaches the floor below which photosynthesis can't run. It's worth being precise about why. A plant doesn't interact with the global carbon cycle. It interacts with the air immediately around its leaves. Tiny pores called stomata open to let air in. CO2 molecules diffuse through those pores into the interior of the leaf. There, a series of enzyme-driven reactions, collectively known as the Calvin cycle, uses that CO2, along with water and light energy, to build sugar molecules. Those sugars power the plant's growth, metabolism, and reproduction. The chemistry of this process has a CO2 dependency. Different plants hit their limits at different concentrations. C3 plants, the group that includes most trees, most flowering plants, wheat and rice, begin struggling at CO2 levels that C4 plants, like grasses, corn, and sugarcane, can still manage. C4 plants have an additional concentrating mechanism that pumps CO2 into the cells where the Calvin cycle runs, allowing them to operate effectively at lower ambient concentrations. But even C4 plants have a minimum. There is a flaw, and the carbonate-silicate thermostat is slowly driving atmospheric CO2 toward it. As that happens, the effects won't be sudden or uniform. Growth rates slow before plants die. Ranges contract before growth stops entirely. A plant community under CO2 stress looks, from a distance, largely like a plant community that isn't until it doesn't. The changes show up at the margins first. Fewer seedlings survive dry years. Recovery after drought or fire takes longer. The upper altitude limit of a forest creeps downward. The outer edges of a grassland thin and become patchy. Productivity falls before area falls. What makes this particularly significant is that it happens on a planet that, from orbit, still looks completely normal. The ocean is still there. Rivers are still running. Rain is still falling. If you could look at Earth from space during this period, you might see a slightly different distribution of green on the continents. But you might not immediately identify anything as wrong. The physical machinery of the planet, its water cycle, its ocean currents, its weather systems, is still operating. What's failing is the biological layer that sits on top of that machinery. A wet planet can be losing the conditions that make it familiar while still looking, from the outside, like a wet planet. There's a deeper irony in this. The mechanism causing the problem isn't a failure of the planetary system. It's the planetary system working correctly. The carbonate-silicate cycle is doing exactly what it's supposed to do, stabilizing surface temperature against a brightening star. Rain is falling on rock. Rivers are carrying dissolved material to the ocean, and CO2 is being drawn down out of the atmosphere. Every step in the process is functioning as designed. The issue is that the design doesn't include a provision for the needs of the biosphere. The thermostat regulates temperature. It doesn't regulate CO2 relative to what photosynthesis requires. Those are two different things, and as the sun keeps brightening, they increasingly conflict. Weathering is, at the same time, protector and threat. Protector of the surface temperature that allows liquid water to persist. Threat to the atmospheric CO2 concentration that allows the living surface to function. For the billions of years during which the sun's output was rising from its young star dimness to its present level, both effects operated together, and the balance was fine. Going forward, the balance tips. The rain keeps falling. The rock keeps reacting. The rivers keep carrying dissolved carbon toward the sea. Each of those steps is individually small and individually ordinary. Added up across a planet and across hundreds of millions of years, they constitute the mechanism through which Earth's own climate system slowly withdraws the gas its living surface depends on. The far future doesn't begin with an explosion. It begins with rain on rock. Let's get specific about what actually fails first. Not the ocean, not the atmosphere in any dramatic sense. The first thing that starts to break down under the slow pressure of a brightening sun and a carbon cycle responding to it is what happens inside a leaf. Photosynthesis is not a complicated concept. Light hits a leaf. The leaf absorbs water from its roots. Carbon dioxide enters through tiny pores on the leaf surface called stomata. Inside the leaf, a series of enzyme-driven reactions uses the energy from sunlight to combine that CO2 with water molecules and produce sugar. That sugar is the fuel for everything the plant does: growth, reproduction, defense against disease. Strip away the chemistry, and what you have is a machine that runs on three inputs: light, water, and CO2. Of those three inputs, the one that's going to run short is CO2. We've now seen why. As the sun brightens, the carbonate-silicate weathering cycle removes more CO2 from the atmosphere to defend surface temperatures. That's the thermostat doing its job. But the thermostat doesn't know, and doesn't care, that CO2 is also the raw material that every photosynthetic organism on the planet depends on. It just removes carbon dioxide, and over hundreds of millions of years, that removal steadily drives down the atmospheric concentration toward a point where the chemistry inside a leaf can no longer run efficiently. Caldera and Casting estimated in 1992 that land plants could face serious trouble, the kind of stress that makes large-scale photosynthesis unsustainable, roughly 1 billion years from now. That estimate assumed a particular set of conditions and has been revisited since. Lenton and von Bloor added biological feedbacks to the calculation and placed the maximum future lifetime of the biosphere at around 1.22 billion years. Graham, Halevi, and Abbott showed that if the weathering cycle responds more strongly to CO2 concentration itself rather than just temperature, plants could survive out to 1.6 to 1.86 billion years. The numbers shift depending on the assumptions. The direction doesn't. What all those ranges have in common is the order. Plants come under serious pressure before the ocean disappears, before runaway heating, before anything that looks dramatic from a distance. The biological crisis at the surface of the planet arrives first, quietly, through a mechanism most people would never guess: the planet's own temperature regulation removing a gas that life needs. The retreat won't be uniform. As we touched on earlier, C3 plants, most trees, most flowering plants, most of the crops that human agriculture has historically depended on, hit their photosynthetic limits at higher CO2 concentrations than C4 plants like grasses, corn, and sugarcane. C4 plants have an additional biochemical mechanism that concentrates CO2 inside the cells where the Calvin cycle operates, letting them function at lower ambient concentrations. So as CO2 falls, C3 plants fail first. Forests retreat before grasslands do. What does that actually look like? Not a curtain falling, not a sudden die-off. Growth rates decline before ranges contract. A tree under CO2 stress still stands, its leaves still open each morning, its roots still draw water, but growth slows. Recovery after drought takes longer. Seedlings that would once have established themselves in an opening fail to take hold. The canopy starts aging without adequate replacement. Productivity falls before area falls. A forest can look largely intact while the processes that sustain it are already compromised. The edges fail first. The higher altitude limits creep down. The drier margins of a species' range become no-go zones. The living world contracts from the outside in, while the core of each remaining habitat continues to function, just with narrowing margins for error. Then, gradually, those margins narrow further. The CO2 floor that C4 grasses can tolerate is lower than the one for trees, but it's not zero. As atmospheric CO2 continues to fall, even the hardiest photosynthetic pathways eventually reach their limits. Lenton and von Blau's biosphere lifetime estimate of 1.22 billion years refers to the point where biological productivity has declined to the level where the living surface can no longer sustain itself as a system. Not the point where the last organism dies, but where the connected, productive biosphere we would recognize breaks down. During all of this, Earth would still look, from orbit, like a water world. The ocean doesn't disappear on this timescale. Clouds still form. Rain still falls. The color from space might be slightly different, somewhat less green on the continents, but the planet would still register as a wet, active world to a distant observer with a telescope. That's the part worth sitting with. A planet can be blue and apparently alive from a distance, while the biological infrastructure that made it significant is failing at close range. The surface water is present, the atmospheric water cycle is running, but the green engine, the network of photosynthetic organisms that has been manufacturing oxygen, building soil, feeding animals, and regulating atmospheric chemistry for hundreds of millions of years, is running down. And this matters beyond just the plants themselves. The oxygen you're breathing right now is a product of photosynthesis, not stored up in rock, not locked into minerals, continuously manufactured by living organisms and continuously consumed by oxidation reactions, animal respiration, and the decay of organic matter. The oxygen concentration in Earth's atmosphere is not a geological given. It's a biological steady state, maintained by ongoing production. When that production falls, the atmospheric oxygen concentration follows. We'll cover that in detail later, but the connection starts here, in the leaf. There's something almost counterintuitive about where this story ends up. The challenge the planet faces isn't a runaway, a positive feedback loop spinning out of control. It's the opposite. It's a regulatory system that works too well. The carbonate-silicate cycle faithfully defends surface temperature against a brightening star. It does exactly what planetary scientists would design a thermostat to do, and in doing so, it starves the very organisms that have been altering the atmosphere, building the soil, and creating the conditions that made complex life possible in the first place. The leaf doesn't know the sun is aging. It doesn't know the carbon cycle is responding to a brightening star. It just reads the concentration of CO2 in the air around its stomata. If that concentration is high enough, chemistry runs. If it falls too low, chemistry slows. At some point, it stops. The future of Earth doesn't begin with something catastrophic. It begins with a narrowing margin inside a thin green surface, repeated across every leaf on every plant on the planet, until there aren't enough of them left to sustain what they've built. As forests lose ground and biological productivity falls, the living world doesn't switch off. It contracts, it retreats, and the places it retreats to tell us something important about what life on Earth actually means once the broad surface can no longer support it. O'Malley James and colleagues studied this kind of late-stage biosphere in detail. They described a sequence of future phases in which complex multicellular life has already declined, but microbial life persists in isolated pockets, refuges. They used the word swan song to describe this phase. The physical reality behind that label is straightforward. Life has retreated into corners, into the places where conditions are still just barely workable, while the wider surface has become hostile or simply too carbon-poor to sustain photosynthesis at meaningful scales. The sequence leading there follows directly from what we've covered. Animals depend on plants or on organisms that depend on photosynthetic organisms. Plants depend on CO2, water, temperature, and light. When CO2 falls below usable concentrations, the base of the food chain weakens. Animals don't solve that problem, they inherit it. Less plant growth means less food, fewer viable habitats, less oxygen production, and fewer stable ecosystems to support populations over time. The large connected surface world that animals depend on starts breaking down before any individual species hits an absolute physiological limit. Microbes are different. Many species live in environments that would instantly kill any plant or animal, deep in bedrock, in hypersaline lakes, in hot springs, in the oxygen-poor water of deep ocean sediments. Some use chemical reactions that don't require sunlight at all, deriving energy from the oxidation of minerals or from hydrogen produced by reactions between water and rock. This metabolic flexibility doesn't make them invulnerable, but it does mean they can survive in conditions where the surface biosphere has long since collapsed. In the far future, they will almost certainly be the last biology Earth carries. But this distinction between microbial life persisting in refuges and a living, productive surface world is one of the most important things to understand about how Earth's habitability ends. A film of microbes on a wet rock face is life. A forest covering a continent is life. Both qualify under any reasonable biological definition, but they are not the same thing for a planet. A microbial film does not change the atmosphere at any significant scale. It does not build soil. It does not feed animals. It does not produce the quantities of oxygen that make the atmosphere breathable for large, metabolically active organisms. A productive surface world, with photosynthetic organisms working across millions of square kilometers of land and ocean, does all of those things simultaneously, and has done so for hundreds of millions of years. The end of that productive surface world is the meaningful end of Earth's habitability. It happens long before the last microbe disappears. What does the retreat actually look like? Not a simultaneous global collapse. The geography of it matters. The hot regions become uninhabitable for complex life first. Too hot, too dry, too CO2 poor. Arid regions follow. The areas that hold on longest are the ones with the best combination of remaining moisture, moderate temperatures, and whatever CO2 can still support minimal photosynthesis, likely higher latitudes, deep valleys, coastal zones with access to ocean moisture. These are not random holdouts. They're the places where the combination of stresses closes in last. As you move further into this future, even those holdouts lose their margins. The geography of life gets smaller and more fragmented. What's left are not functioning ecosystems in any familiar sense. They're isolated patches, each operating with narrower tolerances, unable to sustain the kind of broad biological exchange of nutrients, of organisms moving across landscapes, of atmospheric gases cycling through living matter, that made the productive surface world coherent. Eventually, what remains is the refuge stage that O'Malley James describes. Subsurface pockets of water hosting chomolithotrophic microbes, damp cave walls with thin biological films, organisms living off chemical gradients in rocks rather than sunlight. Scientifically, these are genuinely remarkable, evidence that life's tenacity exceeds the surface conditions that produced it. But they are not the living world we mean when we talk about Earth being inhabited. Here's a useful way to think about what that distinction means for the concept of habitability. The word can be interpreted two ways. One interpretation is simply, does any life exist anywhere on the planet? Under that definition, Earth remains habitable long after the surface world we know has collapsed, potentially for billions of years after, sustained by microbial survivors in deep rock and subsurface water. The other interpretation is, does the planet support large, connected, active living systems that interact with the atmosphere, build soils, sustain food chains, and produce the conditions that complex life depends on? Under that definition, Earth stops being habitable much earlier, when the productive biosphere fails. The second definition is the one that matters when we ask whether Earth will remain a home for the kind of life that exists on it today. And that deadline comes well before the microbes run out of places to live. This also changes what the end of life on Earth means as a concept. In popular discussions, it often gets framed as a single event, some catastrophic transformation that kills everything. The actual sequence is far more drawn out and far more layered. Complex animal life fails before plant life fails completely. Plant life fails before microbial life fails. The surface becomes uninhabitable in the full sense before subsurface environments do. And the loss of the surface world, the forests, the soils, the ocean ecosystems, the atmospheric oxygen, happens not through any single catastrophe, but through a slow contraction driven by CO2 falling, temperatures edging upward, and the refuges that remain becoming smaller and more isolated with time. The last living pockets are not the deadline, they are the remnant. The larger loss, the one that matters for any definition of Earth as a world worth inhabiting, comes far earlier, when the open surface stops being able to sustain the connected biological systems that have defined this planet for the past several 100 million years. Take a breath. That's not a rhetorical instruction. It's the most direct way into what this passage is about. The oxygen in your lungs right now is not a geological feature of this planet. It isn't stored in the rocks or locked into the crust in a way that would slowly release it over time. It is a biological product continuously manufactured by photosynthetic organisms and continuously removed by oxidation reactions, animal respiration, and the decay of organic matter. The oxygen concentration in Earth's atmosphere is not a fixed property. It is a steady state maintained by ongoing biological activity. Stop the production and the removal processes, which don't stop, draw the concentration down. This is the connection that links the earlier sections directly to the air. As CO2 falls below the levels that land plants can use, biological productivity declines. As productivity declines, the scale of photosynthesis drops. Less photosynthesis means less oxygen production. The removal processes keep running. Rocks keep oxidizing. Organic matter keeps decomposing. Ocean chemistry keeps consuming oxygen. But the production side of the balance weakens. The atmospheric concentration falls. Ozaki and Reinhard modeled this chain of events in detail, linking the brightening sun, the declining biosphere, and the future chemistry of Earth's atmosphere. Their estimate: oxygen levels above 1% of today's concentration may persist for about 1.08 billion years, with an uncertainty of around 140 million years in either direction. That number deserves some unpacking. 1% of present-day oxygen levels sounds like it still leaves something, but the oxygen concentration we breathe today, around 21% of the atmosphere, is the product of hundreds of millions of years of photosynthetic activity. 1% of that is roughly 0.2% of the total atmosphere. At that concentration, aerobic metabolism, the kind that powers every animal on Earth, from insects to blue whales, becomes unsustainable. You can't run muscles, maintain body temperature, or support a complex nervous system on that little oxygen. The animal world effectively ends long before oxygen reaches zero. What makes Ozaki and Reinhard's result particularly significant is the timing. Their oxygen collapse arrives before the most severe water loss scenarios. It arrives, in other words, while Earth still has its ocean. The planet can still be visibly wet, still have clouds and rainfall and surface water, while the atmosphere has already crossed below the threshold for breathable air. From orbit, Earth in that era might still look like a candidate for life. Blue ocean, active atmosphere, liquid water. A telescope survey cataloguing planets around nearby stars might flag it as a target. But up close, the air near the surface would be no more breathable than the pre-photosynthetic atmosphere of the Archean, the world that existed before cyanobacteria changed everything around 2.4 billion years ago. This is worth being precise about, because it runs counter to the way most people instinctively think about Earth's future. The intuitive picture tends to jump from habitable planet to scorched, ocean-gone world. The actual sequence inserts a long intermediate phase, a planet that is still physically present, still wet, still active, but biologically hollow. The machinery of complex life has already failed. The living world that produced breathable air no longer exists at the scales needed to maintain it. The reason for this comes down to something fundamental about what oxygen is. It's not storage. You can't fill an atmospheric tank with oxygen and then draw from it indefinitely while the source runs dry. Oxygen is reactive. It bonds with iron in rocks, with carbon in decaying organic matter. with hydrogen in various atmospheric and oceanic reactions. The atmosphere stays oxygen-rich only because photosynthetic organisms keep replenishing it at a rate that matches or exceeds these removal processes. The moment replenishment falls below removal, the balance tips. And it tips quietly, across timescales too long for any generation to perceive. Oxygen also functions as one of the most reliable biosignatures astronomers know of. When researchers look for signs of life on distant exoplanets, atmospheric oxygen is near the top of the list, precisely because its presence at high concentrations requires continuous biological production. Abiotic processes can generate small amounts of oxygen, but not at the concentrations Earth maintains. A planet with 21% atmospheric oxygen is almost certainly a planet with active photosynthesis happening at massive scales. Earth today broadcasts that signal clearly. A future Earth, with its biosphere collapsed and photosynthesis no longer running at planetary scale, would not. The planet would still be orbiting at the same distance from the same star. Nothing about the orbit would have changed, but the living signal would be gone from the atmospheric spectrum. A distant observer comparing observations of Earth across geological time would see, at some point, the oxygen signature simply fade. That transition from oxygen-rich to oxygen-poor atmosphere marks something more fundamental than just the loss of breathable air. It marks the end of the biosphere's ability to significantly alter the chemistry of the planet. For most of Earth's history, life has been a geological force. It changed the atmosphere from a reducing mix of gases to an oxidizing one. It built the ozone layer that shields the surface from ultraviolet radiation. It drives the weathering cycle through root activity and organic acid production. It mediates the carbon cycle through photosynthesis and respiration. When the productive biosphere collapses, all of those influences weaken or disappear. The planet reverts to being driven primarily by geology and physics, rather than by the interaction of geology, physics, and life. The breath, then, is a better clock for Earth's biological future than the more dramatic events that come later. It fails earlier through quieter causes, while the Sun still looks and behaves like the ordinary star it is today. No red giant required, no runaway heating required, just the slow withdrawal of CO2 from the atmosphere, the weakening of the photosynthetic machinery that CO2 fuels, and the gradual unwinding of the oxygen steady state that photosynthesis has been maintaining. The air is the most intimate part of the planet. It's the part of Earth you are in constant contact with, and it's one of the earlier things to go. High above the weather, above the clouds, above the highest aircraft, somewhere around 10 to 16 kilometers up depending on latitude, there's a boundary in the atmosphere called the tropopause. The temperature there is brutally cold, around minus 60 degrees Celsius at the equator, colder still at the poles. That cold matters more than most people realize because of what it does to water. As water vapor rises from the surface through the lower atmosphere, it hits that cold boundary. At those temperatures, most of it condenses. It freezes into ice crystals, falls back as precipitation, and never reaches the stratosphere above. The result is that the upper atmosphere, the stratosphere and above, stays relatively dry. Not perfectly dry, but dry enough that the amount of water reaching altitudes where it can be split apart by ultraviolet radiation is kept to a minimum. This is the cold trap, and it is one of the less celebrated reasons the ocean still exists. Here's the physics of why it matters. Water molecules in the upper atmosphere are exposed to high-energy ultraviolet radiation from the sun. That radiation can break water apart, splitting H2O into hydrogen and oxygen. Oxygen is heavy enough to stay bound to Earth. Hydrogen is not. Hydrogen atoms at those altitudes, hit by UV and heated by the absorption of radiation, can reach escape velocity and drift off into space. Not en masse, one atom at a time, but one atom at a time across billions of years adds up. This process is not a waterfall draining into the void. It's a leak, slow, persistent, operating above the weather where no one can see it, driven by the small fraction of atmospheric water that slips past the cold trap and gets exposed to UV radiation in the stratosphere. Under current conditions, the cold trap is effective enough that the leak rate is small. The ocean has been here for 4 billion years without significant loss. but now warm the planet. As surface temperatures rise, the ocean evaporates more. More water vapor enters the lower atmosphere. The tropopause itself warms slightly as the lower atmosphere does. The cold barrier becomes somewhat less effective. More water makes it through into the stratosphere. More water in the stratosphere means more molecules available to be split by UV radiation. More splitting means more hydrogen escaping to space. The leak rate increases. Casting described a specific threshold for this process in 1991, which he called the moist greenhouse. In the moist greenhouse state, the upper atmosphere becomes wet enough that water loss to space accelerates significantly, not catastrophically, not all at once, but at a rate that becomes geologically meaningful over millions and billions of years. Critically, the surface ocean is still present in this state. The planet hasn't entered runaway heating. It hasn't even lost most of its water. But the water inventory has started declining in a way that's irreversible on any practical timescale. That irreversibility is the key distinction between water loss and the carbon cycle we've been discussing. Carbon dioxide removed from the atmosphere by weathering doesn't stay gone. Volcanism returns it, slowly, over millions of years. The carbonate-silicate cycle is a circuit. Water loss to space is not. Hydrogen that has escaped Earth's gravity is simply gone. No geological process returns it. No volcanic eruption brings hydrogen back from interplanetary space. Every molecule of water whose hydrogen component escapes represents a permanent reduction in the planet's water inventory. Now, the timing here has shifted significantly as climate models have improved. The 3D atmospheric simulations we mentioned earlier, the work of LeConte and colleagues, and of Wolf and Toon, found that realistic atmospheric circulation provides more protection than simpler models suggested. Dry, descending air in the subtropics helps keep certain regions of the upper atmosphere drier than a one-dimensional column model would predict. That regional dryness delays the onset of the moist greenhouse state, potentially by hundreds of millions of years compared to earlier estimates. But a delay is not an escape. The sun keeps brightening. A warmer planet holds more water vapor. At some point, the thermal structure of the upper atmosphere changes enough that the cold trap becomes substantially less effective. When that happens, the leak rate crosses from negligible into something that, over sufficient geological time, matters. The order of all this relative to the events already described is worth being explicit about. The moist greenhouse threshold arrives after the biological losses are already underway. By the time serious water loss to space is accelerating, CO2 has already fallen below what land plants can use. The productive biosphere has already declined. Oxygen levels have already dropped below what aerobic animals require. The planet reaching the moist greenhouse state is not the first warning that something is wrong. It's a later development, arriving on a world that has already been fundamentally transformed in quieter ways. This ordering matters for how we think about the sequence. The moist greenhouse is serious and largely irreversible, but it doesn't define the point where Earth stops being habitable for complex life. That point came earlier, through the CO2 and oxygen story. What the moist greenhouse represents is the beginning of the end for the ocean itself, a much later milestone, and the consequences of a shrinking ocean cascade through the rest of the planetary system. Less surface water means less evaporation, less rainfall, and less runoff reaching rock. Less rainfall means the weathering cycle slows. A slower weathering cycle removes CO2 less efficiently, which changes the balance of the carbonate-silicate thermostat. Less surface water also reduces the geographic range of whatever biology remains, compressing any surviving refuges further. The planet's systems are not independent of each other. Each threshold that's crossed changes the conditions governing the thresholds that follow. Think about the ocean's relationship to the atmosphere in a way most people don't. The ocean's long-term security is not just a function of how much water is sitting in the basins right now, or of gravity holding it to the planet's surface. It also depends on the atmospheric structure above it, specifically on a cold boundary layer high enough above the weather that most people never think about it. That cold layer intercepts rising water vapor before it reaches the UV-rich stratosphere. It has been doing this for billions of years. It's part of why the ocean is still here. As the planet warms under a brightening sun, that protection weakens. Not suddenly, not dramatically, but steadily, in the direction the sun is pushing. The ocean remains for a long time after the cold trap begins to lose effectiveness. But the rate of loss from the top of the atmosphere, which was negligible for most of Earth's history, starts becoming something that planetary chemistry has to account for over geological time. The ocean is held from above as well as below. When the protection from above weakens, what happens below eventually reflects it. Every planet with a surface temperature above absolute zero is radiating energy into space. That's not a special feature of Earth, it's basic physics. A warm surface emits infrared radiation. As long as the rate at which a planet radiates energy outward roughly balances the rate at which it absorbs energy from its star, the climate can find a stable temperature. It might be very hot or very cold, but it settles somewhere. The runaway greenhouse is what happens when that balance becomes impossible to maintain. Here's the mechanism. As the planet warms, from a brightening sun, from increasing greenhouse gas, from any cause, more water evaporates from the surface. More water vapor in the atmosphere means more greenhouse warming, because water vapor is itself a powerful greenhouse gas. More greenhouse warming means more evaporation. More evaporation means more water vapor. The feedback loop amplifies itself, and at some point, the rate at which the planet needs to radiate heat outward to stay stable exceeds what the physical laws of thermal radiation allow for a water-bearing atmosphere. The planet can no longer cool itself. Temperatures climb until the surface ocean evaporates entirely, and the climate settles into a new, drastically hotter state, one without liquid water. This is not the same as the moist greenhouse described earlier. In the moist greenhouse, the surface ocean is still present. Water loss is happening through the upper atmosphere, but the planet remains physically stable with liquid surface water. In the runaway greenhouse, liquid surface water itself becomes impossible. The climate system can no longer maintain a stable state in the temperature range where water is liquid. It crosses into a state where water is only vapor. Casting established this distinction in his 1991 work. The moist greenhouse and the runaway greenhouse are two separate thresholds, with the moist greenhouse arriving first. Later 3D climate modeling, LeConte and colleagues, and Wolf and Toon, found that the runaway threshold is further away than simpler models suggested. Dry descending circulation in a realistic atmosphere delays the transition significantly. But both those 3D results agree on the fundamental point. The runaway state is a real threshold, and Earth will eventually reach it. One thing worth being clear about is what the word runaway actually describes. It sounds fast. It sounds like a sudden tipping point where everything goes wrong at once. That's not what it means here. Runaway is describing the behavior of the feedback loop once the threshold is crossed. The fact that the response reinforces itself rather than correcting itself. The path leading up to that threshold, however, is extremely slow. We're talking about billions of years of gradual solar brightening preparing the conditions. The threshold itself may be crossed over timescales of millions of years. The word describes the physics of what the climate does, not the pace at which the setup happens. This distinction matters because the runaway greenhouse is sometimes treated as the main event in Earth's far future, the dramatic ending that defines the story. But by the time it arrives, the living world has been gone for an enormous amount of time. Let's be specific about the order. Plants come under severe CO2 stress roughly 1 billion years from now, depending on model assumptions. The productive biosphere collapses. Oxygen in the atmosphere declines as photosynthetic production falls. Ozaki and Reinhard estimated about 1.08 billion years for breathable atmospheric oxygen. The moist greenhouse state begins to accelerate water loss to space, with 3D models pushing that threshold significantly later than older calculations, but still well before runaway conditions. Only then, later still, potentially several billion years from now, depending on cloud behavior and atmospheric dynamics, does the runaway greenhouse threshold arrive. By that point, the last complex life has been gone for hundreds of millions of years. The last breathable air has been gone for hundreds of millions of years. The ocean may already have been losing water to space for hundreds of millions of years. The runaway state is not the beginning of Earth's decline into uninhabitability. It is the final physical consequence of a process that began in a leaf, continued through atmospheric chemistry, and now ends with the surface ocean boiling away. Water vapor behaves differently from CO2 in this context, and that difference is part of why the runaway threshold is so significant once it arrives. Carbon dioxide can be removed from the atmosphere by the weathering cycle. It cycles through rock and ocean and returns through volcanism. It has a geological circuit. Water vapor doesn't have that kind of regulating circuit operating at the same timescale. A warmer atmosphere simply holds more of it, period. More of it means more greenhouse warming. There's no equivalent to the carbonate-silicate thermostat pulling water vapor back down when the balance tips. Once the water vapor feedback starts amplifying, the only way it stops is when there's no more liquid water left to evaporate. Venus is a useful comparison here, though it needs to be used carefully. Venus today has a surface temperature of around 465 degrees Celsius, a crushing atmospheric pressure 90 times that of Earth at sea level, and an atmosphere composed mostly of carbon dioxide with sulfuric acid clouds. It is a textbook extreme greenhouse world. If you asked what a rocky planet in the inner solar system looks like after it has crossed the runaway threshold and lost its surface water, Venus is the answer. It exists, it's right there. But Venus is not a blueprint for Earth's future. It orbits at 0.72 astronomical units, significantly closer to the Sun than Earth's 1.0. It rotates extremely slowly, completing one rotation every 243 Earth days. It has no large moon, its geological history differs substantially from Earth's, and its water history is uncertain. We don't know for certain whether it ever had liquid water on its surface, though some models suggest it might have. The specific path Earth takes to the runaway threshold will be different from whatever path Venus took, and Earth will take far longer to get there given its greater distance from the Sun. What Venus does provide is physical confirmation that the endpoint is real. A rocky planet can lose its surface water and settle into an extreme greenhouse state. This is not a theoretical possibility confined to equations. It has happened to a planet orbiting in our own solar system, which we can observe directly. For Earth, the runaway greenhouse represents the physical end of the planet's identity as a water world. The rock remains, the orbit remains. But what made Earth, Earth, the ocean, the water cycle, the liquid water chemistry that life depended on, ends here. The planet still circles the Sun. Nothing of what we would recognize as habitability persists. That's why it belongs at the end of this sequence rather than near the beginning. The first meaningful losses, the ones that determine when Earth stops being a home for complex life, arrived billions of years earlier, quietly, through biology and atmospheric chemistry. The runaway greenhouse is the final stage. It shouldn't be mistaken for the whole story. Throughout this story, we've been giving ranges, about 1 billion years for major plant stress, about 1.08 billion years for breathable oxygen, with an uncertainty window of 140 million years either side, somewhere between 1.6 and 1.86 billion years for plant survival under more favorable weathering assumptions. The moist greenhouse pushed significantly later by 3D atmospheric models, but the exact number still debated. The runaway greenhouse later still, with a threshold that shifts depending on cloud physics. Why ranges? Why can't planetary science produce cleaner numbers? The answer is worth understanding, because the ranges aren't a sign that the science is vague or unresolved. They're actually the opposite. They're information about which parts of the planetary system are doing the most work at each threshold. When a model changes one assumption and the predicted date shifts significantly, that tells you something real. This threshold is sensitive to that variable. The date moved because that variable matters. Understanding which variable moves which threshold gives you a structured picture of the future, uncertain in specific places for specific physical reasons, not randomly uncertain across the board. Clouds are the biggest source of uncertainty for the climate-side thresholds. Low, bright clouds reflect incoming sunlight back to space. High, thin clouds trap outgoing infrared radiation. The net effect on the energy balance depends on the altitude, coverage, and reflectivity of clouds, and how all of those change as the planet warms. A cloud-free model strips this out entirely and gives a clean, tractable baseline. Earth is not cloud-free. Add realistic cloud behavior back in, and the threshold dates for the moist greenhouse and runaway state can shift by hundreds of millions of years. Which direction depends on whether warming drives more low reflective clouds or more high trapping clouds, a question that climate science has not fully resolved even for the near-term Earth, let alone the billion-year future. Atmospheric circulation is another major variable for the water loss threshold specifically. This is what separates 1D from 3D climate models. A one-dimensional column model can't capture the fact that on a real rotating planet, air rises in some regions and sinks in others. Dry, descending air in the subtropics keeps parts of the upper atmosphere significantly drier than the average would suggest. That regional dryness delays the onset of serious water loss to space. When LeConte and colleagues, and Wolf and Toon, built full 3D simulations, they found Earth could remain stable considerably longer than the 1D baseline suggested. The circulation was doing protective work that the simpler model couldn't see. For the biological thresholds, plants and oxygen, the key variable is how the weathering cycle responds. Some models make weathering respond primarily to surface temperature. Warmer surface means more weathering, more CO2 removed. Others make it respond significantly to the CO2 concentration itself. As CO2 falls, the chemical reactions slow, which acts as a self-limiting brake on how fast CO2 can be drawn down. If the second type of response dominates, plants lose their CO2 supply more slowly. Graham, Halevy, and Abbott found that with more CO2-sensitive weathering, plant survival could extend to 1.6 to 1.86 billion years, rather than the roughly 1 billion in Caldera and Canting's original calculation. Lenton and von Bloor added biological feedbacks, the way living organisms themselves influence weathering rates and atmospheric chemistry, and placed the biosphere's maximum future lifetime at around 1.22 billion years. Each of these research groups is essentially pointing a specialized instrument at the same slow process. Caldera and Casting are listening for the CO2 floor below which photosynthesis fails. Lenton and von Bloor are listening for the point where biological feedbacks can no longer sustain the system. Graham, Halevy, and Abbott are probing how sensitive that answer is to weathering physics. Ozaki and Reinhard are tracking what happens to atmospheric oxygen as the biosphere weakens. LeConte, Wolf, and Toon are mapping where the climate-side thresholds actually sit in a realistically complex atmosphere. None of these studies gives you the complete picture on its own. Together, they produce something more useful than any single number, a structured account of which variables control which thresholds. So how should you hold all of this? The most robust thing the science can tell you is not a date, it's a sequence. Plants come under serious CO2 stress before the ocean is threatened. The productive biosphere collapses before the atmosphere loses its oxygen. Atmospheric oxygen fails before the cold trap becomes seriously compromised. The moist greenhouse accelerates water loss before the runaway greenhouse makes liquid surface water impossible. And all of that happens before the red giant phase, which we'll cover shortly. That sequence holds across all the models. Even as the specific dates attached to each step move around, you can push plant survival to 1.8 billion years with the right weathering assumptions, and the oxygen crisis still comes after it, not before. You can delay the moist greenhouse with better cloud physics, and it still arrives after the biological losses. The order is more robust than any individual number. This is actually the most honest way science can speak about a system this complex over timescales this long. A single precise date would be satisfying to report. It would also be false precision, a claim of certainty about a system with real unresolved uncertainties in its cloud physics, its weathering feedbacks, and its biological dynamics. Giving a range and naming what causes the range to exist is more accurate. The uncertainty has a physical address. You can point to it. Clouds move the climate threshold. Weathering feedback moves the plant threshold. Biosphere strength moves the oxygen threshold. These aren't gaps in understanding. They're the specific questions that more detailed future modeling will continue to refine. What doesn't move, regardless of which assumptions you choose, is the direction. The sun keeps brightening. The carbonate-silicate cycle keeps pulling CO2 downward in response. Plants lose their supply. The productive biosphere weakens. Oxygen follows. Water security comes later. Runaway heat later still. Every model, however it differs in the details, agrees on this ordering. That's the thing to carry out of this part. Not a number, not a countdown. A layered future in which each threshold belongs to a different physical process, each with its own clock, its own uncertainty, and its own set of research groups trying to narrow that uncertainty down. The sequence is the guide. The specific dates are still being sharpened. On a clear evening, Venus is often the brightest object in the sky after the Moon. Bright enough that people mistake it for a plane. Bright enough, on a very dark night, to cast a faint shadow. From Earth it looks serene, a steady white point of light, clean and featureless. That appearance is one of the more misleading things in the solar system. The surface of Venus sits at around 465 degrees Celsius. That's hot enough to melt lead. The atmospheric pressure at the surface is about 90 times what you experience at sea level on Earth, equivalent to being nearly a kilometer underwater. The atmosphere itself is composed almost entirely of carbon dioxide, with clouds of sulfuric acid at higher altitudes. There is no liquid water, there is no ocean. There almost certainly has not been for an extremely long time, if there ever was any at all. Venus is worth knowing about in this context for a specific reason. It's not a hypothetical. It's not a model output. It's a real rocky planet, orbiting the same star as Earth, in the same planetary neighborhood, that has crossed into the extreme greenhouse state we've been describing as Earth's eventual endpoint. Everything we've said about the runaway greenhouse and the loss of surface water, Venus is the physical existence proof that this outcome is real. The comparison has limits that matter, and it's important to be honest about them. Venus orbits at 0.72 astronomical units, significantly closer to the Sun than Earth's 1.0. It rotates extraordinarily slowly, completing one rotation every 243 Earth days, which means its day is longer than its year, and its heat distribution is radically different from Earth's. It has no large moon. Its geological and tectonic history appears to differ substantially from Earth's. There's no clear evidence of the kind of active plate tectonics that drives Earth's carbonate-silicate weathering cycle. And its water history is genuinely uncertain. We don't know for certain whether Venus ever had significant liquid water on its surface. Some climate models do allow for the possibility that early Venus, under the younger and dimmer Sun of 4 billion years ago, may have had liquid water. At that point, it was receiving less solar radiation than today. And some simulations suggest that could have been enough to maintain a stable surface ocean, at least temporarily. If that's true, Venus gives us something remarkable. A nearby planet that actually made the transition from potentially habitable to definitively not, and whose current state is the end result of crossing the warm boundary. The details of how and when that happened are still debated. The present condition is not. Here's the physical mechanism that Venus illustrates. On Earth, the carbonate-silicate weathering cycle operates because Earth has liquid water. Rain falls, picks up CO2, reacts with silicate rock, and carries carbon to the ocean where it gets locked into sediment. This cycle is what keeps CO2 from accumulating in the atmosphere unchecked. It's Earth's long-term climate thermostat, but it requires liquid water to run. Remove the water, and the thermostat stops. CO2 emitted by volcanoes no longer has an efficient removal pathway. It builds up in the atmosphere. The greenhouse effect strengthens, temperatures rise further, any remaining water evaporates, and the planet settles into the kind of stable, extreme heat equilibrium that Venus now occupies. That's the cascade. And it's not a hypothetical cascade. It's one that appears to have actually played out on the planet immediately interior to us in the solar system. So what exactly is the right way to use Venus in this story? Venus is useful as a boundary marker. It shows that the warm side failure we've been describing, The loss of water, the collapse of climate regulation, the extreme greenhouse state is physically achievable for a rocky planet in the inner solar system. The inner edge of the habitable zone is not just a theoretical construct. It's a real threshold that a real planet appears to have crossed. Knowing that Venus is there, in that state, makes the physics more concrete. But Venus is not a blueprint for Earth's future, and it's a mistake to use it as one for two reasons. First, the differences between Venus and Earth are substantial enough that Earth's path to any eventual extreme state will look quite different from whatever Venus went through. Earth is at 1.0 astronomical units, not 0.72. Earth has active plate tectonics. Earth has had a living biosphere for nearly 4 billion years that has continuously modified its atmospheric chemistry. Whatever Earth's future looks like, it won't be a close copy of Venus's history. Second, and more importantly for this story, using Venus as the primary image of Earth's future focuses attention on the endpoint and skips over the sequence of earlier losses that are far more relevant to the question of habitability. If the mental image of Earth's future eventually becomes like Venus, that suggests a jump from blue, living Earth to extreme hellscape. The actual sequence is far more drawn out. Plants lose their CO2 supply. The productive biosphere collapses. Atmospheric oxygen declines. The cold trap weakens and water loss accelerates. Only after all of that does Earth approach anything resembling a Venus-like state, and by then, the planet has been biologically dead for potentially billions of years. The danger of leading with Venus is that it compresses that long, layered sequence into a single dramatic image, and in doing so erases the parts of the story that actually matter for understanding when and how Earth stops being habitable for life like us. So the right way to position Venus is at the end of the sequence, not the beginning of the explanation. It's the far physical boundary, evidence that the warm side of the habitable zone is a real place with real consequences, not just a line drawn on a diagram. Earth gives you the detailed path through biology, atmospheric chemistry, and water loss. Venus gives you the answer to, and then what, once all of that is done? From Earth, Venus looks like a point of light. Up close, it's a crushing, superheated, chemically hostile world that will never again have oceans or weather in any sense we'd recognize. That gap between the view from a distance and the reality up close is a good general lesson about planets. How a world looks from afar tells you almost nothing about the conditions actually present on its surface. Earth, viewed from a distance during the biological and atmospheric changes we've described, might still look broadly similar to what it looks like today. Blue, cloud-covered, apparently active. The changes that matter most would be invisible at that scale. The surface conditions would have transformed completely. Venus is the reminder that planets hide what they really are behind their appearance. Earth's future changes are no different. A rocky planet crosses in front of its star. For a few hours, the star dims by a tiny fraction. A telescope records the dip. From that single measurement, astronomers can estimate the planet's size and how far it orbits from its star. And that's a remarkable thing to know from 40 light-years away. It's also a very small slice of the full picture. If the orbit falls inside what astronomers call the habitable zone, the discovery gets announced. A candidate, a rocky world at the right distance. The language tends toward possibility, liquid water perhaps on the surface, maybe the conditions for life. But the orbit is just one frame from what might be a multi-billion-year history. Earth's future makes that gap visible. The same orbit, the same distance, the same star, and 3 completely different planets across time. Early Earth needed heavy greenhouse warming to stay liquid under the dimmer young sun. Present Earth supports full oceans, breathable air, and a productive biosphere. Future Earth will warm past what the carbon cycle can handle, losing its plants, its oxygen, its water security, one layer at a time. Nothing about the orbit changes across those eras, the star does. This is what Rushby and colleagues formalized in 2013, asking not just whether a planet sits in the habitable zone, but how long it stays there. Position is one measurement. Duration is another. A planet that entered the habitable zone recently is a different proposition from one that's been there for 2 billion years. The same coordinates in different stellar eras don't guarantee the same conditions. The age of the star matters as much as its type. A planet around a star slightly older than the Sun might already be past its biological prime, its carbon cycle running down, its vegetation stressed, its atmospheric oxygen declining, even if the orbital distance looks right on paper. A planet around a younger star might not yet have reached its most stable era. The orbital map alone can't tell you where a world sits in its own timeline. This changes how habitable zone announcements should be read. They're not conclusions, they're starting points. The orbital distance tells you where to look more carefully. It doesn't prove oceans, life, oxygen, or long-term stability. The follow-up questions are the ones Earth's history raises. How old is the star? Was it dimmer when the planet formed? Has the planet retained its water? Does it have a carbon cycle, a mechanism that pulls CO2 from the air as temperatures rise? Does active geology return gases to the atmosphere? Has biology altered the atmospheric chemistry over geological time? Every one of these is hard to answer from a light signal measured at interstellar distances. Every one of them can shift the assessment of what a planet in the habitable zone actually is. The same orbital distance can hold a young, wet world still building its ocean, a middle-aged planet with oxygen-rich air and a productive biosphere, or an older world where CO2 has fallen below what plants can use and the oxygen supply is starting to decline. Orbit doesn't distinguish between those states. Time does. Atmospheric gases carry some of that information. Oxygen, at 21% of the atmosphere, is almost certainly biological. Nothing abiotic produces it at those concentrations over geological time, but oxygen isn't permanent. It exists only because photosynthesis continuously replenishes it. A future Earth losing its biosphere would see oxygen concentration fall. A distant observer catching Earth in that era would see a dimming biosignature, not because life never existed, but because the conditions that maintained it had weakened. The signal changes without the orbit changing at all. CO2 tells a similar story. It could be high in an early era, low enough to stress vegetation in a middle era, functionally absent for plant life in a later one. Water vapor in the upper atmosphere can signal a planet beginning to lose its ocean. Every gas in a spectrum is a time-stamped reading of where a world sits in its own history, if you have the context to interpret it. That context is what's hardest to recover from a single transit detection. A photograph tells you something real about a person. The face, the setting, the approximate age. What it can't recover is childhood, health history, or what happened the year before the shot was taken. A planet caught in transit is similar. The dip in brightness gives size. The timing gives orbital period. A spectrum gives atmospheric composition at that moment. None of it contains the planetary biography. The photograph still matters, so does the transit. But neither is the whole story. Earth is something unusual in this context, a planet we can study across its past, present, and projected future. Ancient atmospheric chemistry is preserved in rock and ice cores. Present-day chemistry is measured directly. Future chemistry can be modeled from known physics that isn't available for any other world. For every distant planet, we're working from a single frame and trying to infer the rest. Knowing Earth's trajectory makes that inference sharper. It tells us which questions to ask. Not just, is it in the habitable zone, but is it early, middle, or late in that zone? Not just, does it have water, but has it been losing water to space? Not just, does it show oxygen, but is that oxygen stable, or is it declining as photosynthetic capacity weakens? Earth gives us the list of things to check. The other planet gives us one data point. Stars other than the Sun complicate this further. Red dwarfs burn slowly. A planet around one might stay in the habitable zone for tens of billions of years, far longer than Earth will. But red dwarfs are often violently active when young, and that early radiation can strip atmospheres before the quieter era arrives. The long timescale comes with a different early risk. Larger stars age faster. A massive star's habitable window can be compressed into a fraction of what Earth has experienced. Earth's timetable doesn't map cleanly onto either of those systems. Earth is a worked example, not a universal template. It demonstrates the logic. Star brightens, carbon cycle responds, biology is affected, atmospheric chemistry shifts, water security eventually fails. That logic applies wherever similar physics applies. The specific numbers, roughly 1 billion years for plant stress, about 1.08 billion for breathable oxygen, belong to this star, this orbit, this planetary system. So a planet announced in the habitable zone of a nearby star is still worth attention. The orbital distance is a real constraint. Liquid water is more plausible there than in most locations. That's a legitimate reason to look more carefully. It just isn't an answer. It's the beginning of a longer investigation, and the most important dimension of that investigation isn't where the planet sits, it's when. A planet that meets every criterion, the right stellar type, the right stellar age, the right atmospheric chemistry, active geology, a functioning carbon cycle, is a fundamentally different target from one that meets only the first. Earth's future gives us the language to draw that distinction. The same address, across time, means different things. When a distant world is found in the habitable zone, the first question is location. The second, harder and more important question is, what moment in its history are we catching it in? There's a version of Earth's future that dominates the popular imagination. The sun swells, it turns red, it fills a larger and larger portion of the sky until the inner solar system is unrecognizable. Earth is scorched, or engulfed, or vaporized. The precise ending depends on who's telling the story. It's a vivid image, and it's real. It's also not the first part of the future that matters for habitability, not by several billion years. Schroeder and Smith modeled the red giant phase in detail. When the sun exhausts the hydrogen at its core, nuclear burning will shift to a surrounding shell. The outer layers will expand dramatically. The sun's radius will grow by a factor of hundreds. What we now call the inner solar system will be a different place entirely. The exact fate of Earth under those conditions is genuinely uncertain. As the sun loses mass during this phase, Earth's orbit can drift outward, a gravitational consequence of the sun becoming less massive, but the expanding sun also exerts tidal forces on Earth, which can drag the planet inward, which affect winds, and by how much, depends on details of solar mass loss and the geometry of the interaction that models can constrain, but not yet definitively resolve. Earth might be swallowed. It might narrowly avoid direct engulfment, while still being exposed to conditions far beyond anything the word habitability could encompass. Either way, what's on the surface at that point bears no resemblance to the world we know. But here's what matters about the timing. That happens approximately 5 billion years from now. The earliest biological habitability losses we've described so far, the CO2 stress on land plants, arrive roughly 1 billion years from now. The gap between those two events is 4 billion years. The red giant is not the beginning of the end for Earth as a habitable world. It's the physical conclusion to a sequence that started much earlier, under a sun that looked completely ordinary. The star doing most of the work on habitability is the main sequence sun, the one outside right now. It has already brightened by about 30% since Earth formed. It will continue brightening, not dramatically, not visibly in any human time frame, but steadily, for billions of years before it undergoes any structural change. All the thresholds we've described, from plant stress to atmospheric oxygen to water loss, are driven by that slow, continuous brightening. The giant phase is the sequel, not the plot. This distinction matters because the red giant tends to attract attention in a way that distorts the actual sequence of events. If the ending people hold in mind is a swollen red star incinerating Earth, the implicit story becomes, Earth is fine for billions of years, then catastrophe. That framing buries the actual timeline, where meaningful habitability losses begin far earlier, through mechanisms far quieter than stellar expansion. Carbon dioxide falls below what C3 plants can use, not because the sun went red, but because the brightening main sequence sun drove more weathering than the carbon cycle could compensate for. Vegetation retreats. not because of any dramatic astronomical event, but because the gas supply underpinning photosynthesis has been systematically drawn down. Atmospheric oxygen declines as the biosphere weakens. Water starts leaking from the upper atmosphere as the cold trap loses effectiveness. All of this happens while the sun still looks like it does on any given morning. A yellow-white star of ordinary size, rising and setting, warming the surface, appearing entirely stable. Think of the red giant as the final act of a long story. By the time you reach it, the narrative has already resolved. The living world ended much earlier. The ocean's long-term security was compromised much earlier. The red giant is the physical destruction of the set after the story has already concluded. It's real and it's worth knowing about. But it's not the event that defines when Earth stops being a home. There's a practical consequence to keeping this in order. If you use the red giant as the mental shorthand for Earth's future, the mechanisms that actually determine habitability timescales become invisible. You skip the carbonate-silicate weathering cycle. You skip the CO2 threshold for photosynthesis. You skip the distinction between the moist greenhouse and the runaway state. You skip the cold trap. These are the working parts, the processes that set the real clocks. The red giant doesn't set those clocks. It just arrives after they've run down. The main sequence sun is the engine. It's a star fusing hydrogen in its core at a slowly increasing rate. That rate has been climbing for 4.5 billion years and will keep climbing for billions more. The increase is not fast enough to notice across a human lifetime, or a civilization's lifetime, or even many civilizations' lifetimes stacked end to end. But it's enough to systematically alter the energy budget of a planet orbiting at 1 astronomical unit. It was enough to fix the faint young sun problem. Early Earth received less solar energy than Mars gets today, yet it had liquid water, because greenhouse gases compensated. It has been enough to make Earth's present climate warmer than the early climate, despite lower CO2. And it will be enough to eventually push the carbonate-silicate thermostat into territory where the biological world can't follow. None of that requires the sun to change its appearance. It just has to keep doing what it's been doing. This reframes what the red giant actually represents in the timeline. It's not the cause of Earth's uninhabitability. It's the final physical transformation of the system after uninhabitability is already complete. The star removes what's left of the planet's structure. The habitability losses long before removed what made that structure matter. Knowing this changes which part of the sun deserves attention, not the future giant that's too remote and too final to be useful for understanding the biology and atmospheric chemistry that define when life can exist here. The star worth paying attention to is the one already in the sky, already brightening, already incrementally tightening the conditions under which Earth's living systems operate. That's a quieter and more accurate version of the future. No dramatic swelling, no sky filling with red light, just the same star, aging in the way all main sequence stars age, delivering slightly more energy each billion years, and a planet whose biology and atmosphere are doing their best to respond. The red giant will come. It's written into the physics of how stars work, and the sun is a star. But it comes last. The earlier losses come first, and they come from the light that's already falling on the window. 1 astronomical unit, that's Earth's average distance from the sun, about 150 million kilometers. It's been roughly that distance since Earth formed, through continental shifts, ocean formation, the origin of life, the rise of oxygen, the age of dinosaurs, and the appearance of humans. As a fixed coordinate, it's about as stable as anything in the solar system gets. But stability of position is not the same as stability of conditions. The orbit hasn't moved. What the orbit means has changed dramatically, and will keep changing. Under the young sun, 1 astronomical unit was a cooler location. The sun was putting out roughly 70% of its current energy output. Earth at that distance was receiving less solar radiation than Mars receives today. The planet had liquid water anyway, because the atmosphere at the time was rich enough in greenhouse gases to compensate. The orbit worked, but only because the atmospheric chemistry at the time was suited to that particular level of solar input. Under the present sun, 1 astronomical unit is a different proposition. The planet is warmer. The carbonate-silicate cycle has spent billions of years adjusting atmospheric CO2 downward in response to increasing solar output, acting as a slow thermostat. The result is an Earth with a functioning biosphere, stable oceans, breathable air, and surface temperatures in the range where complex life is possible. The orbit is the same. The conditions are completely different from early Earth. Under the future Sun, 1 astronomical unit will become something else again. The same thermostat that has been protecting the planet will eventually reach its limit. It can keep pulling CO2 downward, but only until CO2 falls below the thresholds that photosynthesis requires. After that, the system loses its biological component, and the cascade we've described so far begins. The orbit stays fixed at 1 astronomical unit throughout all of this. The star keeps brightening. The margin of safety around that address keeps narrowing. That's the core of the whole story. Earth isn't being pushed out of its orbit. The habitable zone is moving, not because Earth moved, but because the star changed. The orbit is the constant. The conditions surrounding that orbit are the variable. A marker placed on a shoreline doesn't move when the tide comes in. The water around it does. What the marker's position meant, safe ground, wet sand, submerged, changes as the tide changes, even though the marker hasn't shifted. 1 astronomical unit works similarly. The address is stable. The stellar environment defining what that address means shifts over billions of years. The sequence of what changes, and in what order, has been the subject of this whole video. It's worth stating it plainly one final time. The first significant pressure comes from the carbon cycle. A brightening sun drives more intense weathering, which draws CO2 out of the atmosphere. That keeps surface temperatures from rising too fast, but it reduces the atmospheric CO2 supply that land plants depend on. Within roughly 1 billion years, CO2 falls below what C3 plants, which account for the vast majority of land vegetation by area, can use. The productive land surface begins its long decline. As the land biosphere weakens, oxygen loses its main source. Atmospheric oxygen is not stored in rock or locked into geological reserves. It's a product of photosynthesis, continuously manufactured and continuously consumed. When photosynthetic production falls below the rate of oxidation reactions in rocks, soils, and oceans, the atmospheric concentration drops. Ozaki and Reinhard estimated breathable oxygen levels persist for about 1.08 billion years, after which the air becomes unsuitable for aerobic animals, while the planet may still have its ocean largely intact. Water loss comes later still. The cold trap in the upper atmosphere, which for most of Earth's history has kept water vapor from reaching altitudes where UV radiation breaks it apart, becomes less effective as the planet warms. More water makes it through. Hydrogen escapes to space. The ocean begins a slow, irreversible decline, slow by any ordinary measure, but permanent in direction. 3D climate models pushed this threshold significantly later than older calculations suggested, but the direction of change is consistent across every model. The runaway greenhouse follows. The planet can no longer radiate enough energy to balance what the sun is delivering. Surface water becomes impossible. What follows that, much later, is the red giant phase, the physical destruction of the planet's structure. Each of these thresholds belongs to a different physical process. Each has its own timeline and its own uncertainties. What doesn't change across the models is the order. Biology first, then atmosphere, then ocean, then the final stellar transformation. The sequence is more robust than any individual date attached to it. Right now, Earth sits inside a window where all of these processes are still in balance. The carbon cycle is working. Plants are photosynthesizing at planetary scale. Oxygen is being replenished. The cold trap is intact. The ocean is full. The sun is still within the range where the planet's systems can answer it. That window is generous in human terms. No person, no civilization, no recorded history comes close to the timescales involved. The losses that will eventually define Earth's habitability boundary are not in any direction that current science, engineering, or policy has any practical bearing on. They belong to deep time, the kind of time that swallows geological periods whole. But generous is not the same as infinite. The window has edges. Those edges are real, not speculative, not theoretical, but grounded in stellar physics, atmospheric chemistry, plant physiology, and the dynamics of weathering. The same sun that makes this planet habitable is the same sun that will, across billions of years, make it progressively less so. Two different clocks run simultaneously. One keeps human time, days, seasons, lifetimes, centuries. On that clock, the sun appears completely stable, the seasons cycle reliably, and Earth's conditions feel fixed. The other keeps stellar time, core hydrogen consumed, solar luminosity increasing, habitable zone boundaries drifting. On that clock, the same sun is a changing object, and the same orbit is being continuously redefined. Neither clock is more real than the other. They just operate at completely different scales. The human clock is the one we live by. The stellar clock is the one the science describes. Knowing about the stellar clock doesn't make the human clock feel different. The morning is still the morning. The air is still breathable. The ocean is still there. The sky looks the same. What changes is the framing around it. A generous present understood as a temporary overlap of favorable conditions rather than a permanent default. That framing isn't pessimistic. A condition can be both genuinely good and genuinely temporary without either quality cancelling the other. Earth's habitability is good. Deep oceans, rich atmosphere, a biosphere that has been running for nearly 4 billion years. It's also temporary in the way stellar evolution makes it temporary, bounded by the slow brightening of an ordinary star and the planet's limited ability to compensate indefinitely. The word temporary can mean a spark. It can also mean an interval so long that mountain ranges rise and erode inside it several times over. Earth's current habitable window is temporary in the second sense. The ending is real. It's also billions of years away, across a span that dwarfs everything human history has produced or could produce. One astronomical unit, the same address it's always been. The meaning of that address has already changed several times, and it will keep changing as the star ages. The orbit is the fixed thing. Everything else, the air, the water, the conditions for life, has been negotiated across billions of years between the planet and its star, and that negotiation still has a long way to run before it concludes. The morning light still falls the same way. It still warms a hand held near the window. It still makes the room feel like an ordinary day. That's the nature of the change we've been describing. It's too slow to see, too large to feel, and real enough to be written into the physics of the star. Earth's orbit hasn't moved. One astronomical unit is the same address it's always been. What moved is the margin around that address. The young sun made one astronomical unit a cooler, harder place to keep liquid water. The present sun makes it a generous one, the right amount of energy for oceans, for weather, for a living surface. The future sun will make it progressively harder for the planet's systems to keep up. The first response to that increased energy comes from rock and rain. Weathering draws CO2 out of the atmosphere, keeping temperatures from rising too quickly. But it does so at the cost of the gas supply that plants depend on. Within roughly 1 billion years, that supply falls below what most land vegetation can use. The living surface follows, forests retreat, productive ecosystems lose their range. The broad green world that has covered the continents for hundreds of millions of years gives way to refuges, and then to less than that. As photosynthesis declines, the oxygen it produces declines with it. The atmosphere becomes unbreathable for animals, while the ocean is still largely intact. Later, the cold trap in the upper atmosphere weakens. More water vapor reaches altitudes where sunlight breaks it apart. Hydrogen escapes to space. The ocean starts a slow loss that no geological process can reverse. Later still, runaway heat. Then the red giant. Earth loses habitability in layers. The green layer goes first. The breathable layer follows. Water security comes later. The planet's final physical transformation comes last. Each loss belongs to a different process, on a different clock, driven by the same slowly brightening star. Right now, the overlap still holds. The oceans are full. The air carries enough oxygen for aerobic life. Rain still dissolves rock and carries carbon to the sea. Leaves still pull CO2 from the air and convert it to sugar. The cold upper atmosphere still intercepts most water vapor before it can be lost. That overlap, ocean, atmosphere, biology, weathering, all working together within the range the star currently provides, is what habitability actually is. Not a fixed property of an orbit, a sustained agreement between a planet and its star, renegotiated continuously through geology, chemistry, and life. The agreement is still running. It will keep running in one form or another for an enormous span of time, long enough that no human framework has a useful way to hold it. But it runs on terms set by the star, and the star is aging. The light outside the window is the same light that sets those terms. Not a warning, not a countdown, just the ordinary output of a star doing what stars do, fusing hydrogen, getting gradually brighter, shifting the conditions of every planet in its reach on a timescale that makes deep geological time look brief. The orbit stayed, the margin moved. It's been moving since the beginning, and the morning looks exactly the same.